investment offer of a 2 crore rupee package over 2 CR. So that's really heartening. Even in terms of bad COVID times, students are really getting a good salary. But of course, by all means, this is one off. There could be many more students who would be drawing a fairly average package, but still, it creates a lot of headlines. So coming back to my subject over here of discussion, like I said, I'll take you down to a journey of in which uh, we have really noticed this. Even day-to-day life, we have noticed quite a significant change when we travel even down the railways. So railways over the period has been pretty slow in terms of taking up the latest research, development, and activities. Take an example of what the axle load of the railway, the goods train has been. If you recall, quite I think it was over a decade ago, or probably that one of the the minister, he overnight he passed an order that the goods train will carry a certain proportion of higher axle load. So at that time it was just 23 ton or so. I think it was made to 27 ton. I really can't pick out remember those exact numbers, but there was a substantial increase in the axle load. Now this created a lot of difficulty because a minister passes an order, it has to be implemented. But how do the engineers think about it? Because if you look at the thousands of bridges which are there in this country, all have not been designed for this kind of axle load. So many of the bridges over the last decade or so, you'll find that there has been continuously revamped because they can't simply knock down and build a new one. So what they have been doing is they have been retrofitting it. They have been increasing their capacity. The foundation columns, the foundation itself have been increased. That is what the structural engineers have been working day in, day out on it. But as a geotechnical engineer, can we really look at it that not only the bridge foundation itself, but in terms of structure, but look at a simple case of a railway track running over an embankment. Now, if the embankment has been designed by, say, 23 ton, as we just mentioned, or an X ton, and we increase this to 1.2 times X, what really happens? Is the embankment able to carry the additional load? uh, as a child, we have seen that you shake up granular particles in a bottle of in a jar. The particles start to pack together. So it's quite common sense that if the embankment has been subjected to railway load for for thousands and tens of thousands and millions of cycles, obviously there would be our thought would say that the embankment would have improved, the quality of the embankment would have improved. So that is why none of the embankments you would see that they have been any of course, if the embankment was in very adverse ground condition, but more or less all the embankments have not been retrofitted. They were there as it is. So now we have a dedicated freight corridor. That's a different issue altogether. But the embankment which were built over a century ago, close to a century ago, or maybe 7 or 8 decades back, they still are very useful. So this was the idea behind it. Can we somehow predict what is the improvement in the strength or the change in strength over a period of time? So our few research scholars, they were quite hardworking research scholars, and I give them the credit for this entire work. In fact, I have shamelessly copied all these slides from them. So the credit goes to those nice people. Okay, so because I was told that maybe there is a bunch of structural engineers in this group, so I thought of putting this slide first just to make us comfortable in what we are speaking about. So if you look at the first top left corner, okay, just a second, please. If you look at the top left corner, you have a figure which shows a uniaxial, so tensile stress strain curve of mild steel. So you have a linear stress strain curve up to a point, and that point usually we call as a yield point, or and below the yield point, if I unload it, it retraces the path. So that's linear elastic for us, but beyond which the plasticity starts to creep in and you see a failure point. So that's a typical which we teach even at the first year undergraduate level. You look at a nonlinear elastic, an example of a rubber. So a rubber would still come back to its original K position, but of course the loading and unloading path are not the same. The stress strain curve for perfectly plastic, of course, this is an idealized material. No material would exist. So it's like, you have a zero strain and suddenly it just starts to deform or fail. So deformation or plastic deformation and failure in this case are synonymous. So they just mean the same, because you don't see a failure point different from the yield point. That's a brittle case, more like a glass kind of thing. The bottom left, many civil engineers would be familiar with. That's again an idealized plot of Moore Coulomb. An elastic, perfectly plastic. This is still, our soil does not really represent this. If you look at the last figure, this is what is represented by our soil. Our soil is non-linear right from the beginning. The curve is non-linear, and it can harden, so meaning the curve can go up, so that we call as a work hardening, or after a peak the stress strain curve will go down and we call that work softening. So these are, the last figure in fact represents our soil, which is a natural material. And as we always say that soil is highly non-linear from either of these study, and it is plastic. So that's important to note. It's non-linear and plastic. That makes this material unique. There's one more, a third point which I would like to add on to non-linear and plastic is the stress dependency. This can be explained by a simple triaxial test. So CD triaxial test is a consolidated drain triaxial test. If you take two samples, so A and B are two samples, and both the samples have the same void ratio. So if I have again a stress strain curve, in this case for soil we define in terms of deviator stress, is still stress strain. We see that the sample A, which is at higher confining pressure, so your cell pressure is high, the curve goes straight up and then asymptotes or becomes parallel to the horizontal axis. Curve B, in fact, has a hump, a camel's hump, and beyond the camel's hump, it just drops. Although both the soil have the same void ratio, the only difference was the confining pressure. If I look at the figure on the right, this is what confining pressure is really explains. It's in fact, it's a simple plot of void ratio versus mean effective stress. So mean effective stress is you could just visualize that it's an average of horizontal and vertical. So you have three-dimensional case, you have two horizontal stresses and one vertical. So three-dimensional, like the first three fingers of your hand. So if you hold them perpendicular, that's what the three axes will represent. So I take an average of them. That's mean stress. And just to add on, because it's the average of the magnitude, therefore it's a scalar quantity. It's not a vector anymore. This makes this plot quite versatile, because now I don't need to worry about the direction. So just in future, if you see mean stress, you should appreciate that this makes our understanding of soil mechanics easier. So we have both the two samples A and B, like we said, at the same void ratio, so they're almost at the same horizontal line. A was at higher stress, so it's there, black dot, and B, red dot, is less. Okay, they are on the either side of the failure line. CSL is the failure line. If you look at this carefully, B will have a tendency to go up. A will have a tendency to go down. So void ratio of B will increase, void ratio of A will decrease. Okay, so that's that tells us that not only the soil is non-linear, okay, plastic, but it is also stress dependent. So these three are pretty important to make this thing, to really understand the soil behavior. Now, when we teach soil mechanics to undergraduate students, so this is these the left hand side are the top left and two sides curves are really typically which we tell them. Now this is similar to your consolidation test or odometer test. Okay, excuse me for a second. So in consolidation test, we have this void ratio versus again mean effective stress. Okay, you have a normal compression line. You load the sample along a normal compression line, and say if you decide to unload, it goes back and somehow takes a loop and comes back again. So that's the what we get from the consolidation test. We idealize this loop to be a straight line. And if I plot this in terms of, remember the figure which we introduced in the previous slide, which was void ratio versus P prime, okay? This is quite similar, what we have. We have plotted the same curve over here. I move from A to B and B to C. Now, B to C is the same as this URL which you have written. In conventional soil mechanics, we say that if you unload from B to C, and then reload from C to B, the path just goes up and down. It just retraces it. I do it like millions and zillions of times. There's no change. Okay, it just goes up and down. Similarly, the same path if I draw on the right hand side from A to B. So A is some starting point. It could have started from the horizontal, somewhere at the horizontal axis, but the thing is it goes leftward. And from B, I decide to unload, it just goes down straight. And then C, if I reload, it goes straight up. It just go up and down. This is conventional soil mechanics. If I want to apply this to our, what the railway minister did, I can't apply, because if I do millions and zillions of load cycle, it will still come back to point B. Point B will not change. So conventional soil mechanics is not able to handle what our esteemed railway minister could handle at that time. Okay, in fact, that esteemed railway minister, I'm not sure if you know, many of you would have guessed it. So that would be a question at the end if you have guessed who the railway minister was. Okay. So coming back to this, what do? We want to change this understanding. So the real problem lies on this slide. If you see, if you look at this axis, the horizontal is the time scale, vertical is the actual stress. So the blue curve which you see, that's one train coming up and down. So for example, the train came up and down, then the second train came, then the third train came. So over the same soil, same material, same point of observation, you have three cycles of sets of cycles of loading. Let's look at the red curve. That's the pore pressure response. So pore pressure response is interesting. So when the first time the train came in, the pore pressure went up, and then when the train went off, it gradually died off. So there is some response in pore pressure. Second time it came in, the pore pressure went up, but it did not go right up to the same point. It went at a lesser point, then died. Third one, lesser. So like that, if I would have continued this number of times, it tries to say that I would reach a kind of a threshold value beyond which probably the pore pressure would not rise so much as it did in the first time loading. So this is interesting. That means with loading, I do see some response, but the thing is, it reaches certain threshold. So yeah, as long as I can model that threshold, I can tell people that, look, this is the soil strength, or this is what you will achieve after, no matter you make the train run another millions of times, but once you reach a threshold, that's the level of change in the soil, whether improvement or not, That is the level of change you will get. So these are the points of really observation. So the first one is the strain accumulated. So soils, they accumulate permanent strains due to the gradual buildup of pore pressure. Okay, that's what this figure is. These pore pressures are described as a function of accumulated strain. So I will again in the next few slides try to show what the strain accumulation has been modeled, or just to put it in this perspective, what the pore pressure accumulation has been modeled, as has been modeled up to now. Okay, and then the last one, of course, is recompression, which I put it as a title of today's presentation, but it's the last thing which which is on this slide, but sorry, on this bullet point, but it's one of the most important one, because all the first 2 points are in fact linked or direct towards the third one. So let's look at the response of the soil. I mean, a typical response. So the 3 figures on the right. If you look at the top figure, I do a number of cycle loads. I see no, absolutely, the strain percent is almost, almost flat. There would be small ripple, because as per each cycle, the ripple would be there. But the scale of this ripple is so small. That's why it's not visible. Okay, but after a sudden cycle, it will be large, maybe 1 or 2 ripple, but then a catastrophic, a sudden failure. This is like is more for loose or soft soils. Okay, this is what happens in loose, soft soils, and we call this as flow type failure. Okay, so as long as you don't reach the end, you're okay with it. Okay, the second one is it's flat, but then it starts to, the amplitude starts to increase, and the failure is huge, it's large. Okay, this is more for dense deposits. Dense deposits will behave like this. So they are the ones which are affected by stress rehearsal, and if I get a chance to speak on it, I'll also tell you what stress rehearsal is in next 30-40 minutes. The last one is the one which lies in between these two. So that's like medium soils, and typically you'll find medium soils embankment to be constructed in this kind of state, which is the last figure. So it just, with the number of cycles, the strains start to accumulate, and up to a threshold point maybe. So this whole thing, my presentation will speak on this. Okay, so we will look at the pore pressure changes and stress changes. We look at some of the degradation models which have been developed, and we will also look at what happens when we have intermittent drainage in between the cyclic loading, meaning one train goes, then before the second train comes in, you have some drainage, or the pore pressure drains off gradually, and then the second train maybe comes in. So we're not going to model the train, but I'm going to just model a cyclic loading on an element of soil. Okay. So we took 3 different soils. The first 2 images are for Bhuj. So Bhuj, as you are aware, 2001 earthquake. So we got those from Bhuj, more or less rounded particles. The last 2 figures are from, again, it's again a sand. It's from Gujarat sand. It's more like an angular kind of thing, and in between is silt from Hisar. So Hisar, so just to give you a background, it's Hisar is where they are coming out with a new nuclear power plant. Sorry. So that's the third one in between. So these are the 3 different soils we kind of tested. All the 3 soils more or less lie within the range of soils which are liquefiable. So that's the thing which we have, but the silt lies slightly away, but nonetheless, that was not the idea. Liquefaction study was not the idea of this whole exercise, because you're not really looking at liquefaction. You want to model the whole state, even if the soil does not liquefy. So these are the photographs taken by, I think this is Aslam's photo. So Aslam is a very bright, was a very bright student. He's graduated a few years back. Now he's in Yonsei, I think, in Korea. I think he belongs to Trishur, if I'm not wrong. Okay. So we were fortunate to have him. So this is again a sample which is prepared by compaction. I mean, I think this is from moist stamped sample. So these are the photographs at different stage, empty cell. This is a split mold. Split mold. Just to tell you, it's just to It's just a temporary support until you fill this with soil. That's filled with soil. Then you put a cap, and then you seal the cap with a tube and apply some vacuum from the top. This is interesting. Only when you apply vacuum within the sample of maybe a small amount of vacuum, then the sample can stand on its own. So you'll see that in this photograph, the split mold has been removed. So you visualize that. I have a leaning tower of Pisa. So I think one of the attendees has a what do you call it? DP. I think they call it DP, right? Your photograph of a leaning tower of Pisa at the back. So that's again a leaning tower of Pisa, but it's made of sand. And visualize it's just standing on its own. This is very. I think not many research students can make a very nice, perfectly cylindrical standing sample. Okay, so that's the first one. And we also did something using a pluviation. So that's pluviator, meaning you rain the sand from the top through a set of diffusers, and the diffusers are made to go up, gradually go up as the sample is formed within this. So this umbrella which you see is just a cover so that all the excess sand does not enter into the mold, but it flows out. So any sand which falls at the border, it just is made to flow out. This is again by I think another research student, Shantan. So this is I think his own innovation and development. So this whole thing is meant to be in a vacuum chamber, but I think in this stage you don't see vacuum because it's open from outside. But what he also did was he modeled this thing using a DEM. So this is again where you have discrete particles of rigid particles, and you see what really can you model that the falling of samples. Remember, so samples are made to fall through a set of diffusers, and the diffusers are stepwise allowed to go up. Okay, as the mold gets filled out. So this is again, it's a moving video. In fact, I don't have a copy immediately, but it's meant to be a video when the particles are made to fall. Now, just 2 points which I want to highlight, even with this procedure is, in case you don't make the pluvator go up, the set of diffusers go up. If you don't do that, what you see is within the sample itself, there is a void ratio difference. So say maybe a point over here and point over there. So what you see is as the sample is formed, okay, if you don't move that plate, because the plate has to move to keep the height of fall constant. If it does not move, you have some sample non-uniformity. And the second thing which you see is if you allow this thing to move, the sample is kind of consistently gets a more uniform sample. So this is again an interesting part over here. The figure which is on the left hand side shows the energy of the falling particles. So if you see the particle which falls at 1 second, it goes down, and roughly 2 seconds plus it's at the bottom. So that's the history of that particular particle. We just traced one. So it goes down, the velocity, it gets a maximum velocity about 3.5 meters per second. I think it's about 10 kilometers per hour. So it's slightly less because it has some air resistance on the way. I think this is modeled with air. And once it rebounds, you'll see a rebound. So this is something we call this as an energetic layer. It's not the same because it falls, it has some energy and this rebound. So some energy is not really captured at the bottom. So because of which you need to have a collar at the top of the sample. Okay. So there are different methods of sample preparation, but the excellent thing is, if I look at the failure line, that's the failure line over here, okay, and it's plotted in another stress space. So Q is a deviator stress, P prime is the mean stress. What you see is all the samples, they reach the same failure line. So that's again the failure line, but in different format. But it just tries to tell us that no matter how you prepare the sample, the failure line is the same. Okay, but if I make samples from pluviator samples and if I do a tamped sample, the difference does lie in how many cycles does it take to liquefy. Because if you want to see whether it has any effect on the cyclic loading, so study of whether the samples liquefy, it's interesting to see. So you, without really going too much into deep, I see that the moist sample, that's the mean line, mean line over there, mean line over there. The up and down is the 5% deviation which you see in the data. So what you see is, if I take a mean line, something like this is 2 cycles. 2 cycles, it takes 0.2 CSR. CSR is your cyclic stress ratio, meaning how much of load you apply. So for the time being, just look at it. It's a normalized factor in what is the magnitude of the cyclic loading you're applying. Okay, so it's, in fact, it's shear stress divided by mean of original effective stress, confining stress. But in your mind, just make it look at, think about it as if it's the normalized of quantity of cyclic loading you're applying. Okay, so it's about 0.2. Look at this. 2 cycles is definitely more than 0.2. I think this was the wrong choice. Let me choose another one. I mean, if you look at it, you'll find that the data over here and over there, the pluviated samples, they give you a slightly more resistance to the cyclic loading. Okay, so this is one point. So if somebody comes to you and says, look, I have prepared this is my cyclic test, I can show that my sand will not liquefy, will not fail under your structure, because it's not going to, my N, when it is 20 cycles, the resistance is high. Okay, your first question should be, how did you prepare your sample? So that would tell you whether the difference in the sample preparation does have an effect. So these are the 3 samples. Usually you do a load control test. So it's plus minus 20 kPa load which you have applied on your strains, which you measure, cyclic strains. It just goes up to there and liquefies. Pore pressure develops up to a point. Similarly, the other 2. So this is just typically, these are the one such test wherein the number of cycles are not more than 100. Maybe the last one has gone up to slightly above 300. And in the left hand side, you will see that even it goes up to 1 million. So this is about a 1 lakh cycle, and that goes really up to close to 1 million. I think it's crossed 1 million over here. So you could see here, 1 second, 1 cycle. So it's about a million seconds. So you do your maths, I think. Million seconds would be approximately how many days? So you can do your maths and see that you ran the test continuously for so many days. Of course, you could have power failure in that, and then you have to start the test again, or you could have a certain data logger problem, and then that creates an issue. But these are the things. So what you see is, sorry. Okay, so what you see is the number of cycles. There are for lower stress ratio, the cycles did go off, but higher stress ratio, they kind of stopped at to maybe 100 cycles, or even up to slightly maybe 1,000 cycles, which you see it crosses 1,000 over here. But the idea of this figure is on the right. What you see is that you see this bottom figure, which is called as A2 curve. In A2 curve, instead of going up to maybe 10,000 cycles at one go, we went up to say 1,000 cycle, then allowed the pore pressure to dissipate, then went up to second cycle, then allowed the pore pressure to dissipate, third cycle, fourth, and so on. So this, in fact, should these curves, I think they're trimmed if I'm not wrong. Otherwise, they should come down to zero over here and go back again. Come down to zero and go back again. Right? So these are different load cycle in short breaks. And the top one is a single one which goes non-stop. It goes non-stop up to 10,000. So we thought, let's look at the difference in these two. What if you have breaks in between? Similarly, the other sample, you have 1, 2, 3, 4 with breaks, and the blue curve goes straight up without breaks. What you see is the stress strain curve after the cyclic loading. So you allowed at the end, you allowed the soil to the pore pressure to dissipate at the end, and when it's all dissipated, you did a conventional triaxial test. So this is a conventional, I think it's undrained, consolidated undrained triaxial test. What you see is in both the samples, the curves are almost the same. So in other words, irrespective of you do, one single jump up to 10,000 cycles, you do small jumps and reach that 10,000 goal, your soil behavior at the end of the day is still the same. Okay. So the very first prediction model we chose was from the, I think this is again was from the literature, where they have a degradation parameter, okay, defined. How does the soil degrade? It's actually called degradation, but that's not a good word to be used, I presume, because the soil is improving. In this case, it's not degrading; it's actually improving. So you what you do is you take the data right up to the failure, you measure the number of cycles to failure, and then you employ a parameter, curve fit the parameter such that you get a curve, something which matches the experimental data. So with this curve, we kind of did is we looked at, can we model the response of the soil. So remember, these curves over here, I think, are the experimental, and the straight lines are the numerical or predicted. So what you have done is you have taken the last point of your experimental, as from the previous slide, we were using the last point when the soil failed and the starting point, and you connected it using a hyperbolic model. This is no good, because you're looking at only the last point, and the last point can tell entirely different story. It cannot even tell you what the story would be in between. So this is what all the curves, they show that there is, of course, you are able to match the last point, but you can't really do much about in between. So you see that number of for all the three samples, the prediction really goes wrong. So the other model other than hyperbolic is the power model. So even power model is reasonably better, I would say. It's better, but at higher number of cycles, it actually is not able to predict the tapering of the pore pressure, how much of the pore pressure increases. I think I did not introduce RU. RU is again a normalized pore pressure. So it's called as excess pore pressure ratio. So when RU is 1, it means it balances the effective stress. So your soil has failed. So that's again just the pore pressure, but excess pore pressure, but a normalized factor. So it has two variables, A and B. You fit in your soil and see that how A and B get it. But in our case, we were fortunate to see that A and B were independent of the soil type, because you see, irrespective of soil type, A and B are the same. But nonetheless, you're not getting a good match, a perfect match. So then comes the slightly revised hyperbolic model, which is an improvement. Let me just tell you, this is again, I think, Nee and all did some work on this. They again try to, what they did was, it's like mathematics, you have a curve and you want to model the shape of the curve without thinking, why this shape has come in the first place. So just trying to model the shape. So there are a number of, even this model, I would say, didn't work very well. Uh, I'll give you a background just in next 1 or 2 minutes on this thing. I need to tell you what this is about. So you're looking at a model, soil model, which is in 3D. This is again a simple soil model in 3D. Remember, we were looking at a Q versus P prime. So deviator stress versus mean stress. So you're looking at this from the back side. So this is how we have been seeing. And we saw that the curve which goes travels from A to B and reload up and down, it just goes up and down. Meaning, suppose our A was somewhere here, it traveled along the curved surface, and then from B I unloaded, so it went inside this thing. So inside meaning somewhere inside, and that's the cross section which has shown. So it went inside and up and down. So in order to correctly model this, what we have done is introduced something like I like to call this as a fudge parameter, because you're fudging or adjusting the result, but it's again a degradation parameter. So when theta equals to 1, I think the next slide explains this better. Please, over here, ignore everything out. This is again, I don't want to confuse you right now. Just look at this theta. And this is the new one, and that's the old one. So when theta equal to 1, the new and old are the same. So meaning this will just go up and down, right? When theta equal to less than 1, the new one will be smaller than the bigger one, old one, sorry. So whenever I do a new cycle, it goes leftward. It will go left. Okay, this adjustment of theta is helpful to make it go left instead of up and down. Okay, so when theta equal to 0, like I said, it just goes up and down here. When theta equal to 1, it's the extreme case. It'll just go, it won't go same path, but it'll go to a new path somewhere here. Okay. Similarly, that's another representation of the same figure, but this time in deviator stress versus P prime. The left one is your void ratio, but in terms, this time it's instead of void ratio, it's written as V specific volume, but it's more or less the same. So we tried, what we did was we adjusted theta between 0 and 1. So this whole thing was done by Carter et al. In 1982, first time. So Carter, what he did was, he said this theta is fixed. He used a fixed value of theta. Okay, that's the thing, fixed value of theta, and he did a lot of tests on clay. So for clay, I think he gave a theta of, I don't remember, was it 0.5 or something, but he used the fixed value. So what we did was we also took the fixed value and saw that let's see if we can plot this. But that figures are not shown over here, but taking a fixed value, we got a very different result. The prediction was very different. So we took a variable theta for in terms of different, the cyclic stress ratio, how much of cyclic load you're applying. So theta was made to vary, or made to vary with CSR, and we saw that there's a relation between CSR and theta. And for all the three soils, there was a range. So we kind of took that value and saw that how the curve fits in. So all these broken lines are the fit curves by Carter, and the continuous line is the experimental data. Okay, for some curves, you see a kind of a slightly reasonable match, but there is again a big offset. Look at this curve; it's a big offset. Big offset. These two curves taper horizontally, but these curves go straight up. Big offset. Okay, so we then, you see, of course this animation is a nice animation. It shows, if you look at the top curve, I think experimental is red, and the Carter and all adjustment is black. I think you'll find that there is a difference, so there is obviously how the pore pressure develops with cyclic loading. This shows a good animation. I'll just skip this. Okay. I think I have another 5 or 10 minutes. Maybe I'll just uh, uh, go to our next point. So we did this, so-called adjustment to bring this thing to down, and it was again based on like the CSR. So this again, it was slightly modified. Now this is again a theta mobilized, or I would say the degradation uh, parameter, which is modified to bring in the effect of both CSR as well as another coefficient alpha. Now the alpha is shown to be dependent on the soil type. I will probably skip this, meaning the particles, whether they are rounded or angular. Now, there is a limitation to this, and I just want you to look at just these 2 points at the bottom. That despite so much of thing, it cannot predict the phase transformation. This is interesting, and I think many people who work with soil dynamics and this kind of thing will be able to understand that when you are about to reach failure, the soil, the phase of the soil, it transforms. Meaning, if you have a dense soil, the behavior in the last few cycles will be like similar to your a soil which is which has a more compressible behavior rather than a dilatant behavior. Okay, so that model cannot be done even with this kind of, because it requires some sophistication, and you're not able to do it. So, but with this modification, of course, we saw that even with literature, you could see some amount of matching, but the matching was kind of only up to a small cycles. But no matter when you do large number of cycles, look at it, you're not able to get a match. So this large number of cycles, another factor was brought in, so that which at small number of cycles it did not have an effect, but at large number of cycles it tried to bring the curve down. So if you look at it, the curve, the broken line, it just tries to bring the broken line curve down. This is interesting because this is what we want to see, that it tries to taper, or it tries to reach a certain threshold value. So with this background, we kind of looked at it that, okay, let's see what is the change in volume of the soil after all the cyclic loading has been done. So, when cyclic loading is done, you want the dissipated pore pressures, you want them to, the soil to either compress so that the pore pressures are gone. What you see is the pore pressure ratio, which is less than 0.4. You see the change in volume is too small. It's 0.001. That's about 0.1%. It's so small. But anything more than 0.4, you see the change in volume is drastically, it increases. So what you're seeing is about this is about, I think, 1%. So you're seeing a large change in volume of the soil. It gives you a feel that if the change in volume is large, so you can in fact expect a significantly change in the soil behavior. So I think this is what Aslam's paper was published. So I'm just going to skip this. This is interesting because if you know a basic thing about soil mechanics, this is just your like your consolidation curve, void ratio or specific volume versus the mean stress. So remember we said if you load the soil and you do an undrained loading, so undrained meaning A to B goes there, and if I allow the pore pressure to dissipate, my conventional soil mechanics will tell me that it goes to a point C, which is there, okay, and that's the where this slope of BC in from consolidation test, we know it is constant. But from A to B, if we do cyclic loading, we notice that when RU is less than 0.75, meaning pore pressure increase is less than 0.75, more or less this slope remains the same. You see this black arrow, more or less they remain the same, but the blue arrow is one which RU is more than 0.75, it shows a steeper gradient. Ideally they should all have the same slope, every one. So BS should be like this, HS should be like this, and okay, third one is not there, but it should be have the same gradient. What you see is the cyclic loading causes the change in the soil property. So this is again unloading. We call this as kappa, and this is interesting. So this change can be even up to over 2 to 4 times the original value. So if you can fit in a curve with this change, so I have the new mean stress versus the old stress. This is interesting. New stress, I can fit in with this change. So this is the change formula which we have. Don't look at the numbers, but just see I can get the new mean stress. That's the interesting point. And the increase in the shear strength. So this is 1 times increase, this is 2 times increase, and so on. So for different curves, it's not there, sorry, I get how much is the strength increase. And somewhere over here, if you look at the left hand side curves, for pore pressure increase less than 0.75, you see that I see about 40, slightly above 40% strength increase, even when my mean stress just changes by about 10%. Similarly, for silt, I get close to double. My strength becomes double, okay, due to cyclic loading, okay, even with a small change in the mean stress. So there's a factor over here which you get from your standard laboratory test. So figure on the right, in fact, don't get bogged down, but it just tries to tell you all this increase. Even if I don't have a cyclic triaxial system with me, I can't do this. If I don't have a good research student, okay, I still can have a routine laboratory test. So these are from routine laboratory tests, and I can still predict what will be my strength increase. So I have over here, which is the increase in the stiffness. Again, the same procedure is followed to obtain the increase in stiffness. And if I move on to the next slide, this is again, I'm sorry, this is something which was different. I thought if I have time, I will introduce this, but I think I'm close to my 70, 80 minutes. So I'm just going to stop and go to my last conclusion, please. I'll skip this and go to conclusion. So, yeah. So, first of all, thank you for staying. Just bear with me for a minute more, and then I'll take up some questions. It says the post-cyclic characteristics of the soil are significantly affected by the pore pressure. So that's important. Whatever pore pressures are accumulated, your behavior, post-cyclic behavior is affected. The soil structure is disturbed because we saw a change in kappa, which is the soil property. So when you say soil property has changed, so people argue that if it has changed, then it should no longer be a property, right? And the last one is the strength is affected by the shape of the particle. So rounded particle is going to be less affected by the angular. Angular particles will have more effect, because even if I do an undrained loading, just look at it. An undrained loading, no matter the rounding particles, they change. They start to rotate, or I won't say translate, but rotate. You're at constant void ratio. The interlocking effect will not be. There will not be a significant change in the interlocking effect. But if I have angular particle and it's still undrained and they rotate, the interlocking is going to change. So that is why in undrained loading, angular particles will still show a large change. So with this, I'd like to thank all the participants for staying. And yes, this floor is open for questions. If you have questions, please do let me know.
Thank you, dear Ashish Vinegar sir, for that informative session. Dear participants, you may ask your questions now. You can interact with Ashish Juneja, sir.
Yeah, before they ask, my question was who was the chief minister? Because I think that was one of the question.
Actually, the railway minister, sir.
Yeah, who? Sorry, who was the railway minister? Apologize. Yes. Anybody? Oh, you people are not interested in politics, I suppose. Never mind. Okay, ask a technical question then.
Okay, sir. I have a question.
Yes.
Sir, is it possible to model this cyclic behavior in a software like Plaxis?
Yeah, Plaxis has a tool. If you have Plaxis with you, it has a tool, and you can model the cyclic loading. It is there in the Plaxis. I'm sorry,
One of our
Piyush Goyal. Somebody is.
sir, one of our yes, one of
Uh,
our participants has commented as Piyush Goyal, railway minister.
no, it's not Piyush Goyal. Sorry, he's the latest one. Make another guess. I'll give you a hint. He was in jail for a considerable period of time because of some scam. And he went to, I think he went to Harvard or somewhere to deliver a lecture. That was the most surprising part. Because after he turned the railways around, he made the railways profitable. That was a very big thing. I think he went to Harvard or somewhere to deliver a lecture, and that was the most surprising part.
I think he was from Bihar.
Yes. So, yes, he is from Bihar. You're right. Lalu Prasad Yadav. So he is the one who made considerable change in the actual load without giving a second thought. Yeah.
Okay, dear participants, you can unmute your mic and you can interact with Ashish Juneja, sir, or you can post your queries on the comment section of the Google Meet.
Okay, I guess they're all tired. Huh? They just want to end this. Okay, maybe you can. They can send a question over email to me if later on they have anything to ask. Okay.
So would you be able to share those slides with us?
I will do something. I do not know because some of this is still in the. Let me do something and let me see what I can do.
Okay, right.
Okay. Okay. Thank you. If there's a
Okay,
question, I can take up. We still have 1 minute before we end. Otherwise, the thing will end up.
okay. Since there are no questions, I take this opportunity to sincerely thank Dr. Ashish Juneja for sparing the time for us, taking this very interesting topic. Thank you, sir. Thanks a lot.
Thank you. You're welcome.
Okay, dear participants, our next session will be handled by Dr. Mallika Shankar. I hope you all know that ATAL has advised to keep at least one session non-technical and to deal with issues related to human behavior, stress management, etc. So we have that session coming up.
Can I just log off, please? Can I leave?
Sure, sir. Sure, sir. Sure.
Thank you.
Thank you. Thank you, sir. Thanks a lot. Okay, dear participants, we shall return at 11:30 a.m. The next session starts at 11:30 a.m. It will be handled by Dr. Mallika Shankar. I will take the session on the title Human Values for Emotional Resilience and Managing Stress, a prerequisite for handling it. Thank you. Thanks a lot.